All right, folks, so dice combinations from the CSES problem set. This is on the dynamic programming category of problems, and it is the first one. So here, I'm not going to read the instruction, you can read the instruction yourselves. So here, what do we need to notice is that we can only have, our dice can have only results from 1 up until 6. So to solve a certain subproblem, we just need the solutions to the last 6 subproblems. So let's just draw this. So let's say we want dpi. We need dpi minus 6, because for all the solutions that I have for I minus 6, so for all the ways that I can construct I minus 6, I just add one more dice roll, which is the dice roll with number 6, and I need to add these ways into my solution as well, because now I have sum of I, right? I minus 6 plus 6 is apparently equal to I. So the same holds for all the other DP solutions from I minus 6 up until, let's just draw the last case here, I minus 1, because for this one I can have a dice roll with result number 1, and then all the solutions that I have for this DP can now be transformed into being solutions for this I, right? So you just check these 6 places and you get the solution for DPI. And so we can progressively just start from I equals to 0, so the sum equals to 0, and move forward, and every time add our result to the next 6 solutions essentially, right? And that would work as well. Or we can calculate the first 6 cases and then look 6 places up backwards and get the result for our case. But the carrying forward sum solution is the easiest to implement. So we're going to implement that. And another optimization we have for this problem is that instead of having a DP array from sum 0 up until sum n, which will need n plus 1 memory spaces, and I think this allows for it 512 megabytes. That's 1 million times 8 per byte, so 4 bytes per integer. 4 times 1 million, that's 4 million, which is around 4 megabytes. So easily it fits inside the memory limit. But just to optimize this and make this easier, we can have a DP array of how many positions? Just 6 positions is what we need here essentially, because we can have only 6. We only care about the previous 6 results every time, right? So if we are looking at, if we are iterating through DPI and we are propagating our result forward, then we need I up until I minus 6. And I minus 6 can be the last one because we can overwrite our position. So we just modulo by 6 the index, and then, yeah, we need essentially just 6 indexes to keep our result. So let's look at the code here. So here I'm just defining this array. The answer is going to have 6 spaces, 6 positions. And then we just read n. So we want to construct some n. For sum 0, we know that the answer, this is the base case, equals to 1, right? So now we're going to start from sum 0 up until sum n minus 1. We don't need to reach sum n because we don't need to propagate the result from that position onwards. We just need to output the result here. So we're going to output n modulo 6. This modulo is not needed. I don't know why I put it there. But anyways, yeah, you just output n modulo 6. So why do we use modulo 6? Is to translate the current position into having only these 6 positions here. We don't have from 0 to n minus 1, but instead we have just 6 positions because we have 6 possible dice rolls. So we start from sum 0 up until sum n minus 1. When we go one by one. For each position we modulo the answer by the modulo. Here I didn't. Yeah, actually I'm doing the modulo here. Anyways, yeah. So we modulo the answer with the modulo, and then we are going to start with the possible dice rolls. So the least we can dice roll is 1, and the greatest we can dice roll is 6. So we are essentially just adding into our position by 1 each time. So in our case, we take the result we have in I plus j, so plus 1 up until plus 5, right? And we modulo this by 6, right? So we look one position to the right. If we draw this here, if we're looking at this position right here, so dp, so we're looking at dpi, right? Then we're going to look to I plus 1, right? And we're going to add the solution we have in our position to the solution we're going to have in that position, in the plus j position. So j equals to 1 in this case. So we're going to add all the solutions we have for this one. We're going to add them to this one, right? And then what we're going to do is to say that this answer is equal to the same value. We just implement the modulo here. Now you might ask, why does j go only goes less than 6 and not plus 6? Okay, this is a very interesting question. Why do we only need to go from I plus 1 up until I plus 5? Like, why don't we also update I plus 6, right? And the reason I don't update I plus 6 in my implementation is that because I plus 6 modulo 6, because I use only 6 places here, already contains the answer we're going to add. Because for the current I that we are looking at, for the current subproblem, this is the first subproblem that can reach with a dice roll of 6, right? So the minimal subproblem that we need for I is I minus 6. So if I'm located in I minus 6, I'm already in the position that I'm going to use for subproblem I, because since I use modulo here in only 6 positions, when I modulo by 6, I'm going to be in the same position. I plus 6 modulo 6 equals to I modulo 6. So for those that are wondering why don't I have one more step. And that's pretty much it. So the complexity here is going to be 5 constant. So it's going to be constant time times O(n), so linear time. So if we go and calculate exactly and roughly how many operations we have, let's say that these are like this is a constant operation, and this is 5 iterations, and this is n. So 5 million iterations, around 5 million iterations, which is quite fast and will pass through the time limit. And then we just output the answer for n, modulo 6. This second modulo is not needed, but it's fine if you put it there. And an empty line, and that's it. That's the solution for dice combinations. So if you got stuck and this video helped you, please leave it a like, subscribe to the channel. The solution will be down in the description below, and I will see you in the next video.